Okay, let's unpack this. Imagine you're diving into, creating videos just from text prompts.
Right, using those big AI diffusion models.
Exactly. And you type in the perfect description, hit generate, and the video comes out, well, maybe a little weird.
Like jumpy, or maybe it doesn't quite match what you asked for. That's off.
Or just fuzzy. Then you try again, same exact words, and get something completely different, maybe even worse sometimes.
It's a common frustration, definitely, what's going on there.
Well, that's what we're digging into. Is there a way for the AI to get smarter about how it even starts the process?
The starting point, the noise seed.
Precisely. This deep dive is all about a really fascinating new paper from Samsung Research. It's called Model Already Knows the Best Noise, Bayesian Active Noise Selection via Attention and Video Diffusion Model.
Quite a title. Sounds like it exact issue, the huge impact of that initial random noise.
It does. They propose a framework, ANSE, that tries to deal with how unpredictable that noise seed is, how much it affects the quality, the consistency, everything.
Okay, ANSE. So our mission today is to get into how this model-aware approach actually works.
Yeah, exactly. We need to understand ANSE, figure out this BANSA score they talk about, and see what it means for making better videos, hopefully faster too.
Sounds good. We've got the paper, notes, FAQs, figures, all the pieces. Let's do it.
All right, so first things first, the core challenge, this initial random noise in text-to-video, or T2V models.
Yeah, it seems almost counterintuitive, but that random starting point is incredibly critical. It's like the primordial soup the video grows out of.
And the exact flavor of that soup determines, well, everything.
Pretty much. The paper hammers this home, right in figure 1. Same text prompt, same model, but you get these drastically different videos solely because of the noise seed.
And it's not just, minor visual tweaks. The paper says the seed affects the actual quality, the smoothness over time, temporal consistency.
And critically, how well the final video actually matches your text prompt alignment.
Right. They say, due to the iterative nature of the diffusion process, the choice of initial noise profoundly influences video quality, temporal consistency, and prompt alignment.
It's the foundation for that whole step-by-step denoising process that creates the video. Get the foundation wrong, and well.
So if everyone knew this noise seed was so important, what were people doing about it before this ANSE approach came along?
Well, previous methods often tried to fix it from the outside, so to speak. The paper calls them approaches using externally designed priors.
Externally designed, meaning they weren't asking the model itself what it thought.
Exactly. They were imposing ideas from outside, like assuming certain patterns or frequencies in the noise might be better based on some theory.
Okay, like trying to make the noise look a bit more structured from the start. I think I saw mentions of things like Freenet or Freq prior.
Yeah, those worked in the frequency domain. Or Piyoko, which tried to create noise that was already kind of dependent between frames to encourage smoother video.
That feels somewhat logical. Try to start with noise that seems like it should lead to a good video. But what were the catches?
2 big ones, according to the paper. First, like you said, they weren't using signals from inside the model. They, quote, fail to leverage internal signals within the model that indicate which noise seeds are inherently preferable.
So the model might know which starting points feel better to it, but these methods were ignoring that, kind of flying blind.
Pretty much. And the second big issue was purely practical. They were slow. Really slow.
How slow?
Evaluating these noise seeds often meant running the whole video generation process multiple times. The paper mentions multiple full diffusion passes, sometimes even 3 full sampling passes.
3 full passes just to pick the starting noise? That sounds computationally brutal.
It was. Table 1 shows it could lead to a 200% increase in inference time.
Wow, okay, 200% extra time just for the setup is a lot, especially when the video generation isn't exactly fast to begin with.
Absolutely. Which leads us nicely into the real innovation here. ANSE and BANSA, this is where they flip the script.
Right, the model-aware approach. Tell us about ANSE's active noise selection for generation.
So ANSE is their framework. And the key, as you say, is being model-aware. It's grounded in Bayesian uncertainty, not external guesses. It tries to figure out the model's own level of confidence or uncertainty about different starting noises.
Bayesian uncertainty. So probabilities, model beliefs. How does it measure that?
Through the core component. BANSA, Bayesian Active Noise Selection via attention. This is like the heart of their contribution.
BANSA, okay.
BANSA's job is to measure uncertainty inside the model, specifically by looking at the attention maps during the generation process.
Attention maps. Why attention? Isn't the model outputting noise predictions? Why not look there?
That's a really sharp question, and it's key to their innovation. While the output is noise, the attention layers are where the model is doing complex reasoning. It's where it aligns the text prompt with visual elements and tries to keep things consistent across frames.
Ah, okay, so attention is where the semantic understanding and structure emerge.
Exactly. The authors say, we inspect estimate uncertainty in the attention space where alignment between text and visual tokens naturally emerges during generation. It's a smarter place to check if the model feels confident about building from a particular noise seed.
So it's like checking the model's internal workspace to see how confidently it's connecting the bots based on the starting noise.
That's a great analogy. And they connect this BANSA idea to existing concepts in machine learning, specifically active learning. You might know the BOLD score.
Vaguely. Isn't that used in classification to find data points the model is unsure about?
Precisely. BOLD measures uncertainty in the final class predictions. BANSA adapts that core idea for generative models, measuring uncertainty in the attention maps instead.
How does it do that? Measure uncertainty and attention.
It essentially looks at how much the attention maps change if you slightly perturb the process. It calculates multiple stochastic attention samples for one noise seed and measures the disagreement between them. High disagreement means high uncertainty.
Okay, so you sort of put the attention mechanism while it's looking at a noise seed, and if the attention patterns jump around a lot, that seed is probably bad.
You got it. The BANSA score quantifies that disagreement and confidence across multiple attention samples. And here's the key finding, which might feel a bit backwards at first. A low BANSA score is what you want.
Low score is good. Usually high scores mean better performance.
I know, it feels weird. But think about it. Low disagreement means the model's attention is stable, consistent, confident, even with those small perturbations. The paper states a low BANSA score indicates that the model is more confident and certain in its attention,
which empirically correlates with coherent video generation. Okay, I see it now. Confidence and certainty in attention means a better starting point. Figure 1 showed that, right? The better video came from the lower BANSA seed.
Exactly. That figure's a prime example. So the whole goal of the ANSE framework is to sample a bunch of candidate noise seeds, calculate the BANSA score for each, and pick the one with the minimum score. Figure 3 illustrates that score amend step clearly.
Find the seed the model feels most sure about via its attention mechanism.
Precisely. They even back this up mathematically with something called the BANSA zero condition proposition 1. It basically shows the score only hits 0 when all the attention samples are identical, representing complete confidence and consistency. So minimizing the score pushes you towards that ideal state.
Okay, that makes sense conceptually. Low BANSA equals high confidence equals better video start. But calculating this for multiple seeds, needing multiple attention samples per seed, didn't we just say previous methods were too slow? How did they make this practical?
Ah, yes, the efficiency challenge. This is the other really clever part of the paper. They came up with 2 main innovations to compute BANSA quickly enough for inference time.
Okay, let's hear the tricks. Making cool ideas usable is half the battle.
First, stochastic approximation via Bernoulli-masked attention, instead of running the whole model forward multiple times with dropout to get those stochastic samples.
But so it's slow.
They inject randomness directly into the attention calculation itself, using simple binary masks, 1s and 0s.
How does that work? Just randomly masking connections?
Kind of. Figure 3 gives a visual. Right before the softmax in the attention calculation, they multiply by a random mask. This lets them get multiple different stochastic attention views from just one pass through the main model layers. Super efficient.
Okay, one forward pass gives multiple attention samples. Much faster. What's the second efficiency hack?
Layer selection via cumulative BANSA correlation. Think about these massive T2V models, tons of layers, lots of attention maps. Calculating BANSA across all of them is still computationally heavy, even with the masking trick.
Right, and maybe you don't need all the layers. Maybe the important uncertainty signals are concentrated somewhere.
Exactly their thought. Not all layers might be equally informative. So they developed this correlation-based truncation strategy.
How does that work?
They compute the BANSA score layer by layer, adding them up cumulatively. Then they check how strongly this running total correlates with the final score calculated using all layers. They find a point maybe after D layers where the correlation hits a threshold, say 0.7 Pearson correlation.
So they find the minimum number of early layers needed to get a score that reliably tracks the full score. And 0.7 correlation is reasonably strong.
Yep, strong enough. It means the score from just that subset of D layers is a good proxy for the whole time. This significantly reduces the computational cost without sacrificing the effectiveness. Table 5 shows the results are almost identical using the truncated set versus all layers.
Clever. So Bernoulli masking is multiple samples per pass, and layer truncation reduces how much attention you need to examine per sample. Combined, this makes it fast.
Fair, relatively speaking. What's the actual overhead? The paper reports only a marginal increase in inference time of about 8% for CogVideo X2B and 13% for Cogvideo X5B.
8 to 13%, compared to the 200% we heard about earlier. That's negligible in practice for many applications.
It's a massive improvement in efficiency. Makes the whole approach viable.
Okay, so it's fast. But does it actually lead to better videos? What did the experiments show?
They tested it thoroughly on big models, Cogvideo X2B and -5B, using the standard vBench benchmark.
And the results? Did the scores go up?
They did, consistently. Table 1 lays out the numbers. ANSE improved both the quality score and the semantic score on vBench. For the 2B model, the total score went from 81.03 to 81.66. Similar gains for the 5B model, up to 81.71.
So statistically, better quality and better alignment with the prompt.
Exactly. Meaningful improvements on a tough benchmark.
Numbers are one thing, but did the videos look better? Any cool examples?
Oh yeah, the qualitative results in the figures are pretty striking. Figures 1, 4, 8, 9, 10 show lots of examples.
Like what?
Well, remember the corgi from figure 1. Much sharper, happier looking with the ANSE seed. Figure 4 had a stormtrooper that was just static before, but with ANSE, it was actually marching.
Nice.
Other examples showed better anatomy for animals, like zebras, and just generally more coherent and stable motion. Figure 10 may be the most direct comparison.
What's in figure 10?
It shows videos generated from the same prompt using a random seed, the seed with the absolute worst BANSA score from their candidate pool, and the seed with the best lowest BANSA score.
And the difference is clear.
Night and day. The best BANSA seed produces a video that's vastly superior, clearer, more stable, makes more sense. The worst BANSA seed often results in something totally broken or full of weird artifacts. It's strong visual proof that minimizing BANSA works.
Wow. Okay, so better scores, better visuals, minimal extra cost. Did they do any other checks to make sure their method was solid? Like why BANSA specifically?
They did. Good papers include ablation studies to justify design choices. Table 2 showed BANSA with their Bernoulli-masking beat other ways of measuring uncertainty. Table 3 suggested around 10 attention samples was a sweet spot.
And how many noise seeds did they need to check?
Figure 6 indicates that performance kind of plateaus after checking about MEVA 10 candidate seeds. You don't need to check hundreds.
Okay, those refine the parameters. But what about the core idea that low BANSA is good?
The crucial test. That's in Table 4, the reversed BANSA criterion. They deliberately picked seeds with the highest BANSA scores, maximum uncertainty.
And
the video quality tanked. The scores went down significantly.
that's pretty compelling evidence. Choosing the most uncertain seeds makes things worse, confirming that choosing the least uncertain, lowest BANSA seeds makes things better.
Exactly. It strongly supports their central hypothesis.
It all sounds really promising, almost too good to be true. Any downsides or limitations they mention?
They're realistic about it. It's not magic. ANSE chooses the best starting point, the initial noise. But as they say, it does not directly affect the generation process itself after that initial step.
Meaning, if the base model just isn't good at generating, say, complex interactions or specific objects, ANSE can't fix that.
Correct. Figure 7 shows an example where, even with a low BANSA seed, the generated horse looks unnatural. The model itself had limitations ANSE couldn't overcome.
So it helps you get the best possible result from the model you have, but it doesn't improve the model's fundamental capabilities.
Precisely. They also acknowledge there's still a gap between estimated attention-based uncertainty and perceptual semantic quality. BANSA is a good proxy, a practical surrogate, but it's not a perfect predictor of exactly how a human will perceive the final video.
Makes sense. It's an internal model signal, not a direct measure of final human judgment. Still sounds incredibly useful, though.
Definitely.
Okay, so let's wrap this up. What's the big picture takeaway from ANSE and BANSA?
The main takeaway is that we can significantly boost text-to-video quality and reliability by being smarter about that very first step, choosing the initial noise. And crucially, we can do this efficiently by looking inside the model, using its own attention uncertainty as a guide.
ANSE and BANSA give us a principled, model-aware way to find that best guess starting point.
Right. It leverages the model's internal state, specifically the confidence and consistency shown in its attention maps, without needing expensive external computations or heuristics. It's adapting concepts like Bayesian uncertainty and active learning for the generative video setting.
And the efficiency scales make it practical. This feels like a different approach to improving AI generation, doesn't it?
It really does. The authors frame it as a potential new inference-time scaling paradigm. Instead of just throwing more compute at the generation steps or making models bigger, you improve performance by making a more informed choice right at the very beginning.
Guided by what the model itself seems to prefer.
Yeah, that quote, "This work highlights the potential of inference-time noise selection guided by internal model signals," really captures it. It's a smart way to get more out of existing models.
So for the listener, what's the relevance if you're building these models?
This gives you a concrete technique to improve reliability and quality with low overhead, a way to leverage internal signals you might have ignored.
And if you're just using these tools,
Hopefully, approaches like ANSE becoming standard means you get better, more consistent videos more often, less time hitting generate again and again, hoping for a lucky seed, more predictable results closer to your prompt.
right, getting what you ask for more reliably.
That's the goal.
So this deep dive into ANSE and BANSA really shows how listening to the model's own internal confidence, how steady its attention is when faced with that initial noise, can unlock better quality right from the start.
Yeah, it's fascinating.
It really makes you wonder, doesn't it? What other internal signals are hiding inside these incredibly complex models? Signals we could potentially use to guide them, make them perform better or more predictably, without the massive cost of retraining them from scratch.
It's a great question to ponder. What else does the model already know?